Hello, welcome back to this series leading up to trigonometry as we continue to work our way through college algebra. So today we're going to talk about quadratic functions. We'll talk about the characteristics of a parabola, specifically the vertex, the axis of symmetry, the x and y intercepts, and the maximum or minimum value depending on which way the parabola faces. We'll talk about the different forms of writing a quadratic function. There's a vertex or standard form versus a general form and how to convert between the two. We'll look at finding the equation of a quadratic function if we're given the vertex and some other point that lives on that graph. And then we'll talk about just straight up graphing some quadratic equations. So we'll start with the characteristics of a parabola here. And here's just like a summary of kind of all the different bits and pieces. I've written down what the vertex form or also called the standard form, and we'll see these kind of definitions on the next page, and the general form in a little bit more detail. But this is just to give you a sense of what they look like. Oops, and I forgot my squared on that portion already, so I need to make sure I get that 2 in there. That's very important. Just kind of looking at the different values or the different characteristics here. For the vertex, it's going to be this point down here, at least on this example, and we would call this point HK, where h would be the x-coordinate of the vertex and the k would be the y-coordinate of the vertex. Here it looks like our vertex is at 1, -4. So thinking about this as a function, as we will moving forward, we could think about an input of 1 and an output of -4, and that being kind of the minimum value of this parabola. If the parabola was going the other way, then that vertex would be a maximum value. So in a lot of the applications that we'll want to do involving quadratics is we might be looking to find, okay, where is this parabola going to min out, going to hit its minimum value, or where is it going to max out? Where is it going to hit its maximum value? So that is what I mean by this is where the maximum and minimum values occur. We also have this other kind of formula that might be hard to read. It's kind of small here, but we'll talk more about this on the next slide. The axis of symmetry is just this line that passes right through the middle of the parabola and splits it right in half. The parabola is symmetric about its axis of symmetry. This is helpful because if we're trying to graph a parabola, anytime we find, for example, something on the left or on one side of the parabola, we know that there is going to be an equivalent point directly on the other side here. So that can be helpful as we are graphing, and it will be helpful later on when you get into calculus if you're needing to find the area under a parabola. Knowing that it's symmetric about its axis of symmetry can help save a little bit of time. It is just the h value, the x coordinate. If we look at this line, this is just the line x equals whatever x value it is passing through. So that's always going to be h. It's always going to be the x coordinate of the vertex. Though that is not a coincidence that they're both called h. That is very much on purpose. The x-intercepts are going to be the points where it passes through the x-axis. And notice that the y values here, the output values, are 0. So in both cases, that's not where I was trying to go. In both cases here, this is mapping back to 0, which means the output is 0. The inputs are whatever they need to be. Those are the x values. So here I've just called them x1 and x2, but we know that the output values, the y values, will be 0. That is just the way that it is when you look at the graph. There could be 0 y-intercept. So if we had maybe a parabola that lived entirely above the x-axis, then you could imagine, oh, there would be no x-intercepts here. It could also be that maybe the parabola just touches the x-axis and bounces back up, which means there would still, or in this case, there would be just one x-intercept. Or it could be the case that we have here where it lives below the x-axis and we get 2 x-intercepts. But those are the only possibilities. So there will either be 0, 1, or 2 x-intercepts. And then the y-intercept is the spot, I already kind of highlighted here, the spot where this passes through the y-axis. Here, if we look again, the x value we can always know will be 0. Just kind of looking back at the x-axis here, that point is always 0, comma, wherever it passes through. So here it looks like it passes through 0, -3. And remember that these y-intercepts and the x-intercepts, I didn't write down what they are, but this one is 3, 0, this one is -1, 0. We always write them as points. The intercepts are points. Since one coordinate is always 0, sometimes we kind of focus on whatever the numerical value is, but we should always be representing our intercepts as points. Okay, so that kind of gives us more or less the characteristics of the parabola here. We'll take a little bit more in-depth look at some of its parts. So we'll start by talking about the general form versus the vertex or the standard form. I call it vertex form. Lots of books call it standard form. But the vertex form, I think, is kind of the most helpful. It's kind of, I think about it as kind of like the y equals mx plus b version of a quadratic, because it tells you a lot of information just by looking at the formula here. So here we have f of x is equal to some constant value a, that's not equal to 0, multiplied by x minus h, quantity being squared, plus k, where hk is the vertex of the parabola. So just by looking at the function, we can already tell where the vertex lives. And then moving forward, we'll know something about that a value, which will help us as well. Like I said, also called standard form. And then the general form of the quadratic is in this also familiar form of ax squared plus bx plus c. If you're thinking about like the quadratic equation, this is the form that we would need it in to use the quadratic equation if we were trying to set this equal to 0 and solve for x, where a, b, and c are real numbers, and a is not equal to 0 again. Here the vertex is not stated in the function, but we can find it coordinate by coordinate. So the x coordinate, the h, is going to be equal to negative b over 2a. And then remember that if we have some point, h is the input, instead of writing k, I could just write f of h, and that would be the output. So that is what I'm doing here. Now h is equal to negative b over 2a. So this k identity looks like a nightmare, but really it's saying find out the value of h. It's going to be just some number like 2 or like 1/2, and then plug it back into the function and evaluate it. So it turns out to be not so bad, even though the way that they're being represented here kind of look a little messy. Okay, but why does h equal negative b over 2a? And that is a great question. So we'll investigate it here a little bit, and it'll help motivate kind of what we want to do here on this next example. But if I look at this general form of a parabola, so if I look at ax squared plus bx plus c, and I want to try to put this into the vertex form, into the standard form, what I could try and do is complete the square here. So I'm just going to kind of work this out and maybe not explain too much, but on the next example we'll talk about it in more detail. But if I want to complete the square here, the first thing I'm going to need to do is factor off an a from just the first two terms. This is the area where I'm going to focus on completing the square. So I'm going to have x squared plus b over a times x. I'm going to leave a little space to complete the square, and then I've got plus c at the end here. So right now these say exactly the same thing. Think about multiplying the a back in, and we get right back to where we started from. But to complete the square, what we do is we take a look at the b term, the b over a in this case, and what we want to do is divide that in half and then square it. So what I'm going to do is divide that in half, which will give me b over 2a, and then I want to square that. But I can't just go add this portion in green without also subtracting that right back off. So essentially what I'm doing here is just adding a funky form of 0. But I'm not just adding on b over 2a squared, I'm actually adding on a times b over 2a being squared. So this is a little funky, don't worry about it too much. I'm not really going to worry about the adding and subtracting. I'm really just going to focus on the front portion here, but I just want to make sure I'm keeping things legit, so we do get this at this point. Okay, and now focusing on completing the square on mostly just this front portion here, we're going to get a x plus b over 2a all being squared. And then we've got this portion at the back end, which is going to end up being c minus b squared over 4a. You can check my algebra on that if you'd like, but that is what we get, which means that I could rewrite this as a x minus negative b over 2a to really force this into the form that we want, plus c minus b squared over for a. But really what we see here is that by forcing this to be in the vertex form, that the vertex must be negative b over 2a. We could also see that the k must be this value over here, but it's typically a little bit easier to just plug whatever negative b over 2a is back into your function and solving from there. So just a little reason for why that h value is negative b over 2a. All right, so we're going to use that idea of completing the square here to actually put some of these in their vertex form. So the idea here is to add and subtract the same value. So we can add and subtract, I don't know, p and minus p. If p is just some number, doing that doesn't change the value. We're just adding and subtracting the same thing. I just picked the variable p just because it was the first one I thought of. But okay, so the idea here is that we want to focus on the first half to complete the square, and then we will just add and subtract whatever value that we need to complete the square. So we will take x squared minus 10x, and then we'll leave a little space to complete the square, and then we'll add 18. So if I'm trying to turn x squared minus 10x into a perfect square, what we do is we look at the middle term, we'll take a look at the negative 10, we'll divide that in half, and we'll square it, and this is the value that we will both add and subtract. So this is negative 5 squared, which is 25. So what we're going to do is add 25 here. So if I just associate those, that turns into a perfect square. But then I better subtract off 25, because I can't just add 25 without changing the value. If I add 25, I need to subtract the 25 right back off. So that tells me that I can write this as x minus 5. We have a minus here separating them. So I've got x minus 5 squared. And then 18 minus 25 is minus 7. So this tells me that once I have it in this form, that the vertex is at 5, negative 7. I could have also used that negative b over 2a to figure out the vertex, but this is also a way to do it. All right, in this next example here, we're going to need to be a little bit more careful because we have this 2 value, this coefficient in front of the x squared term, which we need to deal with. So the first thing that we're going to do is factor off the 2 from just the first couple of values here. These are the ones that we complete the square on. This minus 7 at the end is just kind of coming along for the ride. So I'm factoring out 2, and I'll get x squared plus 4x. I'll leave some space to complete the square, and then I'm going to add the minus 7 at the end here. Okay, so again, to complete the square, what we do is we look at the middle term, and here that is positive 4. We're going to divide that in half and then square it, and then this will be the number that I'm going to both add and in a sense subtract, but we need to be a little bit careful. But this is going to give me 2 squared, which is 4. So plus 4, and then I didn't just add 4 to the left or to this parenthesis here. What I actually did was I added 8, because that 4 is going to get multiplied by this 2 as well. So what I really need to do is add, if I added 4, I need to subtract 8, because I didn't actually add 4, I added 8. So I will subtract 8 off of the other side as well. Okay, and then simplifying from here, this is going to give me 2x plus 2 squared minus 15. And this tells me that if I needed to find the vertex, that it would be at the point negative 2, negative 15. Remember that if we really want to write this specifically or explicitly in its vertex form, then it's always x minus whatever value it is being squared. So here we can see that it is negative 2 and then minus 15, minus 15. All right, so looking at this next example here, we are going to find the equation of a quadratic if we know its vertex and some other point. So I think before hopping into this, we'll just get a quick sketch going here. Whoops. And I don't know if I'll be able to fit it all on the graph because of this negative 21, but I can certainly try. I know that my vertex is going to be at 1, 2, 3, 1, 2, 3, 4, so something over here. And that's got another point at -2, and then -21's like down here somewhere. But I know that it's going to look something kind of like that. Okay, and this is the point 3, 4, and then there's going to be some other point over here. That's going to be -2, -21. Okay, so now what we want to do is just use what we know the equation of a general quadratic to be, or a standard quadratic. We could maybe pick our form, but I'm going to use this standard form, this vertex form, because I think that it's nicer. So I'm just writing that out, a times the quantity x minus h squared plus k. And the first thing I'm going to do is just look for things that I can substitute in from what I know. I know the vertex is at 3, 4, which means that for h and k, I can substitute a 3 and a 4. So just kind of writing my formula back out, I've got y equals a times x minus 3, all being squared, and then plus 4 at the end. So I've got my vertex in here, color-coded at green. Now what we can do is we can use this other point to plug in for the x and the y value. And once we do that, the only thing left will be this a variable. We can solve for a, and then we should have it. So if I plug in -21 for y, and I plug in -2 for x, so writing this kind of all back out, I'm going to have a, -2 is x, I'm still subtracting off 3, and I'm still adding 4 to the end here. And now there's just arithmetic to do, a little bit of algebra. So -21 is, oh, and I forgot my squared over here, very important. -21 is equal to a times -5 squared plus 4. If I subtract 4 from both sides, I'm going to have -25 is equal to a times +25. And now I can divide both sides by 25, and I will get that a is equal to -1. So now I know all of the pieces of the equation here. And if I want to write this out, kind of going from here, now I know what a is. What I'll get is y is equal to -1 times x minus 3, all being squared, plus 4. So there we go. We were given the vertex and some other point, and we can kind of use those step by step to solve for a and get the entire equation here. All right, and last we will practice just straight up graphing a quadratic equation. So we'll use the formula here and find all of its parts that are listed to the side, and we'll use those to put them on our graph. So maybe what isn't as nice is that this was given in the general form instead of the vertex or standard form, which is a little bit easier, but we can still do this because we have that relationship between h and k and a, b, and c. So here, if I write this out explicitly, we can say that a is equal to +1, b is equal to -5, and c is equal to -6. Looking at the signs here is also important. In the general form, there's always addition everywhere. So if I want to find the vertex, first I will look for the h value, which is -b over 2a. Here, b is going to give us -5 over 2 times 1. So this is going to give me 5/2. That is going to be the h value. So if I'm looking at my graph here, I can go to 5/2 is 2.5. So here's 1, here's 2, here's 3, here's 5/2, kind of right in the middle. Now I need to find the output of this. So what I'm going to do is look at f of h. So this is finding k. Maybe I should start with that. To find the k value, this is f of h. So I'm going to look at f of 5/2. Okay, and then plugging 5/2 into the original formula here is going to give us 5/2 squared minus 5 times 5/2 minus 6. So this is going to give me 25/4 minus 25/2 minus 6. If I get some common denominators here, maybe just move this kind of up over here. I might have to erase some of this to make some space, but this is going to give me 25 over 4 minus 50 over 4 minus 24 over 4. So 25 minus 1, negative 49 over 4, I believe. Yeah, negative 49 over 4, which should be about negative 12.25. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 0.25 is right around there. So I could label this vertex as 5 halves, negative 49 fourths. Okay, there's my vertex. So next we'll find the axis of symmetry, which we already did. The axis of symmetry is the line x equals h, which is going to be the line x equals 5 halves. So let me go make some space here. Okay, so that means that I can write an axis of symmetry. Maybe I'll just do that in pink here, but that's just going to go right through there. So now any points that I find that live on the left, I can find a symmetric one on the right and vice versa. Okay, so next we will look for our intercepts. So maybe we'll do this in green. So looking for the x-intercepts. The x-intercepts are when the y value is equal to 0. And so I always like to write this down as a reminder, but what this tells me is that I need to solve x squared minus 5x minus 6 equals 0. So I think that this should factor here. And this should be x, let's see, minus 6, x plus 1 equals 0, which will tell me that x equals 6 or x equals negative 1. But we are finding points. So the points that we found here are 6, 0, and negative 1, 0. So we can get those on our graph here. So we're going to have a point at negative 1, and we're going to have another one at 3, 4, 5, 6, over here at 6. And those are our x-intercepts. And then lastly, we will get our y-intercept. Oh, notice that this parabola has 2 x-intercepts. We noticed before that there might be 2, there might be 1, or there might be 0, depending on where this lives. So here we have 2 x-intercepts. There will always be a y-intercept, and the y-intercept is when x is equal to 0. So finding the x-intercept means that we are solving for y now. Y equals 0 squared minus 5 times 0 minus 6. So in almost the very first slide we looked at, we saw that the y-intercept will just be the point 0c, and we're talking about this c. And this is the reason why, that once we plug in 0, the result is we just get y equals whatever the c value is, which here that is negative 6. So we know that the y-intercept will be at the point 0, negative 6. So 1, 2, 3, 4, 5, 6. Here we've got negative 6. We can use the axis of symmetry to get another point. If I went over 2.5 to the left, I can go over 2.5 to the right and find another point symmetrical on the other side. And now I can draw my graph, which is going to look something, well, let me try a little bit better, see if I can get through that point. Something kind of like that. So here we've got the vertex, we labeled that. We've got the y-intercept labeled. Here we've got the x-intercepts at negative 1, 0, and at 6, 0. And we've got the axis of symmetry, which is this line, x equals 5 halves. So there we've got it all together. We have our quadratic graph by finding the vertex, using the axis of symmetry, and then finding all the x-intercepts and y-intercepts. All right, from there I will leave you to practice, which means it's time to do homework. Please let me know if you have any questions, and see you in the next one.